Thanks for tuning in to the first video in a series that the MI team is putting together to celebrate and to announce our new HCR HiFi encoder, a new reagent that enables multiplex IF in a way that users have never really seen before. And so to kind of kick things off, I wanted to take a minute to sort of pull back the curtain and invite you guys to see how do we think about the question of what does the world need in a new protein imaging product or a new protein imaging approach? And so that these slides will just help set that up. And then in future videos, you'll learn how um, our our new reagent is used and how it can fit into your existing workflows, and then also just some tips and tricks using it, as you get started. So we've seen over the years and even before us that RNA imaging has grown in terms of how routine it's used in research and then increasingly in clinical practice. But even still, protein imaging is the gold standard for, not just in the clinical setting, but across the entire sort of pipeline of biological research, ranging even to the early biology stage when people are studying embryogenesis and those kinds of questions. Really protein targets are the things that people care about detecting, and RNA is often seen as a surrogate or a sort of added value on top of protein imaging. And today, regardless of where your research lies, pretty much all protein imaging methods rely on incorporating these secondary antibody-based approaches. And so in general, how that works is a user or a researcher has a primary antibody that will bind to the target of interest, and they'll detect it by using a species-specific secondary antibody that will bind to it, and then use that to generate signal. And there's some key limitations to that I'll go into in a couple of slides. But within this gold standard of protein imaging, most of the methods that are popular today incorporate these secondary-based approaches. And what we've seen as companies have come forward with new methods, usually dubbed as spatial biology, there's significant drawbacks, even though they offer some really cool benefits over direct labeled secondaries or enzymatic secondaries that still do prevent their broader adoption. And so pulling back the curtain a little bit, I want to show, I'm also a former consultant. So for me, this is a plot that makes sense. And I want to walk through the different technologies that are out there and how we analyze them and how we think about where their place is in the market. And so on the x-axis, we'll characterize them by how easy or hard are they to customize. So if you have a 4-color panel of protein markers that you work with, how easy or hard is it to swap one of those primaries out for a different primary? Or how easy or hard is it to swap 2 of the colors, even within keeping the same primaries? And then on the y-axis, we'll do something similar, but for how easy or hard is it to multiplex? So if you take that same 4-color panel, how easily can you add a 5th color? So to get started, we'll look at sort of the most OG method there is, which is just using direct labeled primaries. So, kind of taking a break from what I just said on the previous slide, this is not a very popular approach today. But the way it works is your primary antibody itself is directly labeled with fluorophores, and that will generate signal once it binds to a target. And some of the benefits with this approach are that you can do same species primaries together. So if a user has multiple mouse or multiple rabbit primaries, they can work together because they all carry spectrally distinct fluorophores and they can be imaged in parallel. So it's one incubation. And the fundamental downside or downsides with this is that they're pretty hard to customize. So if you have your own unmodified primary, it's not hard to label it, but it's also not necessarily the easiest thing in the world either to do well. And there's no amplification. So if your primary antibody can carry 2 or 3 fluorophores, you can't really amplify it beyond that. So certain channels can be really tricky to work with, especially the shorter wavelength ones like green or yellow. So today, this is not a very widely used approach, but it is sort of the most simple version of immunofluorescence. So the first of the 2 really dominant versions or methods that are used today are direct labeled secondaries. So technically very similar, but instead of labeling the primary antibody, the primary is actually unmodified. And then instead, what is labeled is a secondary antibody that is just a species-specific molecule. So it's nice because you can make this thing in bulk. It can just be a common bulk reagent that a lab keeps in stock. And it can basically bind multiple secondaries to a primary, and you get a little bit of an amplification boost out of that, maybe 2 to 5 times brighter than a direct labeled primary. And that's really the benefit here, is for many cases, that's enough amplification to get workable signal, and then people have strategies to mitigate autofluorescence. And the other benefit is that you don't actually have to do anything to the primary antibody. So you can work with unmodified primaries. You don't have to worry about, did my labeling change the binding affinity of this antibody now? All of those concerns are gone. But the fundamental problem with this approach is that you can't use multiple same species primaries together. So if a user has 2 mouse primaries that they'd really like to use, with this approach, they just can't do it. So there is a subset of users who work with tissue sections where they can do this chemical stripping and cycling that is quite damaging to tissue, but beyond those very specific sample types, it's not a workable solution. So it's actually much harder to multiplex. And instead, you have to find primaries that are raised in all kinds of different species. The second version of a secondary-based product are what we call enzymatic secondaries. And so with this approach, it's the same secondary, but instead of being labeled with a fluorophore, it's instead carrying an HRP or some enzyme that can then be used for depositing a fluorochrome or a chromogen on top of it. And in general, these are a little bit easier to work with because typically they're only designed for tissue sections. And so within that sample type, there are many branded products that a user can buy to do this. And so, it has many of the same drawbacks as direct labeled secondaries, but in practice, a little bit easier to work with because you also get a much higher performance boost in the amplification. So these are some of the traditional approaches. In terms of what the industry calls spatial biology, it really centers around this concept of barcoded antibodies. And by that, what I'm referring to is the concept of conjugating an oligo barcode or an adapter onto an antibody itself, and then using that barcode as your readout. And so the first version of this is an unamplified version with a barcode. So the nice thing about this is that you can tackle same species primary incubation because the barcode is now the thing that differentiates between the different primaries, not what species was that primary raised in. And so, the beauty of this approach is also the thing that makes it very challenging, which is typically you need to find a commercially available menu of primary antibodies to select from. And if your primaries of interest are all within those menus, then you're in a good place. But if it's not, it's really hard to conjugate an oligo to an antibody sort of in a high fidelity way. There's, conventional conjugation requires tweaking the chemical reaction itself. It requires purification so that you don't have unconjugated primary floating around in your cocktail of antibodies. There's a lot of work that goes into making these primaries perform well. And then on top of all that, because there's no amplification, it faces most of the same problems that direct label primaries face in terms of not being able to see it very well in more autofluorescent channels or samples. And then the final approach that we're going to put here is barcoded primaries that incorporate amplification. So they use that barcode to then trigger some downstream amplification like HCR, although nobody has done it with HCR just yet. And these tend to not really tackle the fundamental problem with these spatial methods because they still rely on conjugating oligos to antibodies. And typically what we've seen in the market in terms of branded products is the amplification is usually an enzymatic approach, which has other issues that make it a little bit less robust overall. And then finally, for us, the other problem with many of these methods is that they're all limited to fluorescence, except for enzymatic secondaries. And for MI, we spent a lot of time trying to bridge the gap between clinical deployment and studying embryogenesis, to put it simply. And if you don't have a way for a bright field readout to be possible, there's really not as much scope for clinical impact. So this is how we view the market in terms of technologies, not necessarily in terms of products. And a really important thing for us is to not come out with something that is just swimming in the sea of these other technologies that doesn't really have any differentiation. And so internally, we target how do we make something that fits in the top right quadrant of this kind of plot and stands alone and is like our RNA fish products, where all we have to do is talk about how it works and why it works, and that's enough. And users are so compelled that they pick it up and try it, and they go from there. And so I want to show a little bit about how we've done some work that gives us confidence that we could pull this off, and then what we've developed to sort of enable this kind of differentiated multiplex IF approach. So the first part of it is HCR Gold, which is our sort of our amplifier system for parallel multiplex of up to 10 RNA targets, or in this case, protein targets, within any sample. So today it's hundreds and hundreds of different species and any prep of that sample, whether it's thin tissue, cells in suspension, or even whole mounts. And platform agnostic, meaning it can be run manually with a really nice sort of human-friendly protocol, and then also adapted easily to all kinds of automation platforms that are out there. And so I want to give a reminder, a refresher for anyone who may not have seen or may not remember how HCR works, but this is the core that enables HCR Gold today. And so I'll go through it a little bit quickly, but for any HCR Gold amplifier system, we have these three components: H1, H2, and I1, which is the initiator. And we engineer H1 and H2 so that they don't directly interact with each other. All that needs to happen is they're cocktailed in a sample. And when that happens, an initiator, which is bound to a target, can trigger this polymerization, the self-assembly of these individual H1 and H2 monomers into this long polymer in situ. And the best part about this reaction is it's very simple. So in practice, this is a one-step reaction, regardless of the number of targets that a user is studying. It is background suppressing, which means sort of internal to this design, we prevent hairpins from just polymerizing and generating tons of amplified background. It's isothermal at room temperature, is optimized to work in salt buffer, and is enzyme-free. It is a really, really advanced amplifier that's just very, very easy to use. And the magic component that we're really excited to launch is the HCR Hi-Fi Encoder, which is an entirely new class of reagents that enables a user to bring any primary and really easily functionalize it so they can use it with an HCR Gold amplifier. So the encoder enables rapid, site-specific encoding of any antibody, and we're encoding it with the ability to trigger HCR Gold amplification, which can then support high fidelity amplification of up to 10 targets in parallel, and uses the HCR Hi-Fi platform to do really, really good background suppression with high degrees of amplification. So I want to show a little bit of data before wrapping up today's video. And so the way we characterize a performance is by looking at specificity and sensitivity. And on the specificity side, what matters to us is to bring the same clinical grade specificity that we expect with our RNA-ish products to an IHC or an IF product using the Hi-Fi architecture that we've built. So here's an example of a tissue section. This is an FFP human tonsil tissue. And on it, we've added or incubated a rabbit isotype. So something that should not bind any antigens within this tissue section. And to detect it, we've used an enzymatic secondary. This is a commercially available kit that is actually used in clinical practice quite routinely. So it's validated. And then we've deposited a brown chromogen, a very sensitive chromogen. And you can basically see no brown here if you take my word for it. There's nothing here. And that's performing exactly as it should. This kit with this isotype should really show clinical grade performance, and it really does. So if we take this same isotype and we encode it with one of our initiators, and we give it the ability to amplify with HCR Pro, which is our sort of our ultra sensitive chromogenic sort of clinical grade amplifier, and then use the same brown chromogen, we should see the same thing, and we actually do. And for those of you who are watching who've ever worked with conjugated antibodies, this is kind of a shocking result, especially with bright field readouts where background can't be sort of tuned away by adjusting the settings of the image. So this is how we validate specificity, that it performs really well. It doesn't generate amplified background. The encoded antibody doesn't somehow get stuck and trigger amplification downstream. It really just performs as the unmodified primary does on the left. And when we encode primary antibodies, we also need to be sure that we're not changing the affinity for the target antigens. And so to make that demonstration, we do something very similar, but instead using real targets that are actually present. And so here's a very similar setup, but now the primary is not a rabbit isotype. It's a very commonly used clinically relevant clone of PD-1 called Cal-20. And this is what it looks like when you use a classical enzymatic secondary with a brown chromogen. And if you take that exact same PD-1 primary and you encode it with one of our initiators and use HCR Pro, you get very, very similar expression. In fact, when we've been showing this to people or qualified people and you don't label them, it's hard to know which one's which. And that's kind of the goal. Here's another example of a routinely used, like not a obscure random clone we found that happened to conjugate well, called CD8 with an enzymatic secondary kit, and then HCR Pro, again, showing very, very consistent staining patterns. Here's CD3, the SP162 clone, enzymatic secondary on the left, and HCR Pro on the right. We could do this all day, but we're going to stop it here. But suffice to say that every primary we've encoded just behaves as it did as an unmodified primary, which is really the bar we're trying to hit. And the beauty with this approach is that the encoding is actually done prior to incubating in the sample. And so multiple primaries can be encoded separately and then combined for straightforward multiplex, which we can do with HCR Gold, even with same species primaries. And here's an example of a 3-color IF, where we've taken 3 different primaries for CD68, Ki67, and pan-CK, and coded them with 3 different HCR Gold amplifiers, and then amplified them. And the benefit with HCR Gold over even a direct labeled secondary is you see anywhere from 5 to 50 times improvement in performance over a direct labeled secondary approach. So it really stands alone in a sort of performance category of its own. Here's an example of the encoder being used by one of our beta testers in whole mount fruit fly. And so here they used a primary with just one of our encoders, and it shows how quickly it can just be used on their first try. And before I wrap it up, I just want to share that when we create these products, we don't forget about what we already make. And so it's important for our team to engineer new things to work with things that we already make. And so in this case, we enable best-in-class co-detection. So here's an example of using HCR Gold amplification to amplify both RNA and protein detection in the same sample. So polar 2A and RNU6 as RNA targets, and then CD8 as a protein target. So we're really excited for people to get their hands on these kits. We're, the model is very similar to how users will have learned how we like to operate, which is there's no dedicated hardware. We just sell reagents. The pricing is very reasonable and accessible. And we're really excited for people to be able to say goodbye to their secondaries and really get started with the encoder. So that's where I'm going to end today. We will have a couple of more videos that'll come out a little bit later showing how to use the encoders in practice. How can you actually get started with your own primaries? And then also some tips and tricks and FAQs as we go through this early access period. But thanks again for your time.